In September 2022, astronomers pointed the newest, most expensive space telescope ever built at a single star and captured something genuinely historic. That's not the only unimaginable thing James Webb has confirmed since it started operating. Stick around, because the real discoveries here are stranger. Stars are almost unimaginably brighter than the planets orbiting them. Trying to photograph a planet directly next to its host star is a bit like trying to photograph a firefly sitting right next to a lighthouse beam from miles away. That's why, for most of the history of exoplanet science, astronomers have relied almost entirely on indirect methods. Watching a star's light dim slightly as a planet passes in front of it. Measuring a tiny gravitational wobble in a star's position caused by an orbiting planet's pull. Direct images, actual photographs of a planet as a separate point of light next to its star, have always been extremely rare. On September 1, 2022, NASA announced that James Webb had captured exactly that. A direct image of an exoplanet called HIP 65426b. The planet itself had actually been discovered years earlier, back in 2017, using a ground-based instrument called SPHERE on the European Southern Observatory's Very Large Telescope in Chile. But Webb's image, using infrared wavelengths, ground-based telescopes simply can't see clearly through Earth's own atmospheric glow, revealed new detail nobody had captured before. HIP 65426b is a gas giant somewhere between 6 and 12 times Jupiter's mass. It's young by planetary standards, estimated at only 15 to 20 million years old, essentially a newborn compared to Earth's 4.5 billion years. And it orbits its host star at a genuinely enormous distance, roughly 92 times farther out than Earth orbits the Sun. That huge separation is actually what made the image possible in the first place. With that much distance between the planet and its blindingly bright star, Webb's coronagraphs, specialized instruments designed to block out a star's light artificially, were able to cleanly separate the faint planet from its host. And faint is an understatement. HIP 65426b is more than 10,000 times dimmer than its own star in near-infrared light. Sasha Hinckley, the astronomer at the University of Exeter who led the observation team, called the result a transformative moment, not just for Webb, but for astronomy generally. Aaron Carter, a researcher at UC Santa Cruz who led the image analysis, described the achievement more simply. He said obtaining the image felt like digging for space treasure. That's genuinely what makes this discovery remarkable. Not that the planet itself defies physics. It's a fairly ordinary, if unusually distant and young gas giant. What's extraordinary is that humanity now has a real, verified telescope capable of directly photographing worlds orbiting other stars, opening the door to studying smaller, cooler, more Earth-like planets in the years ahead, something scientists have been working toward for decades. That's one confirmed, remarkable finding. But it's far from the only one. James Webb was specifically built to see further back in time than any telescope before it, by capturing infrared light that's been stretched out by the expansion of the universe itself, a phenomenon called redshift. The farther back you look, the more that ancient light gets shifted toward longer, redder wavelengths. Almost immediately after Webb began operating, it started returning images of the very early universe that genuinely puzzled cosmologists. Among the strangest were a class of objects that researchers nicknamed little red dots. These are small, extremely compact, unusually red objects showing up repeatedly in Webb's deep field images, dating back to when the universe was only a few 100 million years old. And they've turned into one of the most actively debated puzzles in modern astrophysics. Initially, some researchers wondered whether these little red dots might represent an entirely new, unexpected population of extremely massive, extremely early galaxies, packed full of stars far sooner after the Big Bang than standard models predicted was possible. As more data came in and researchers studied these objects using Webb's spectroscopic instruments, capable of reading the specific chemical and physical signatures encoded in their light, a different picture began emerging. Many of these little red dots appear to be powered, at least partly, by rapidly feeding supermassive black holes at their centers, actively growing far earlier in cosmic history than existing models of black hole formation expected. That's still a genuinely significant unresolved puzzle. Current theoretical models describe two main pathways for how supermassive black holes could form in the early universe. Either growing gradually from smaller seed black holes formed from the collapse of massive early stars, or forming more directly and rapidly from the collapse of massive early gas clouds. The little red dots Webb keeps finding seem to require growth rates on the faster end of what either model comfortably predicts, or possibly hint at formation pathways scientists haven't fully worked out yet. Researchers are still actively debating exactly what these objects are and how they manage to grow so large so early without invoking anything beyond standard physics. This is genuinely one of the most exciting open questions in cosmology right now, precisely because nobody has a fully settled answer yet. Multiple research teams, using different methods and different subsets of Webb's data, continue publishing competing analyses, refining mass estimates, and testing different formation scenarios against the evidence. That's real functioning science in progress. Not a mystery hidden away by any agency. And not evidence the universe is somehow broken. It's exactly the kind of unresolved, actively investigated puzzle that shows a powerful new instrument is doing precisely what it was built to do, revealing things nobody fully expected and forcing careful, ongoing scientific investigation to figure out why. Webb has also delivered striking evidence supporting one of general relativity's stranger predictions: gravitational lensing, in some remarkably precise ways. Gravitational lensing happens when a massive foreground object, usually a galaxy or galaxy cluster, bends the light from something directly behind it, due to the way mass warps spacetime itself, exactly as Einstein's equations describe. In certain, very specific alignments, that bent light can form a complete or nearly complete ring around the foreground object, called an Einstein ring. In 2023, researchers using James Webb identified one of the most complete, well-defined Einstein rings ever observed, cataloged around a galaxy now referred to informally as JWST R1. The alignment required for a ring this precise and complete is genuinely rare, requiring the background and foreground galaxies to line up almost perfectly from Earth's specific vantage point. That's not evidence of anything artificial or designed. It's a direct, visually striking confirmation of exactly what general relativity predicts happens when mass this concentrated sits directly along our line of sight to something farther away. Astronomers use discoveries like this one specifically to measure the mass of the foreground galaxy, including its invisible dark matter content, with a level of precision that's difficult to achieve through other methods. It's also worth talking about Webb's deep field images more broadly, because they represent some of the most information-dense, carefully studied pictures ever produced in the history of astronomy. In July 2022, one of Webb's very first published images showed a region containing the galaxy cluster SMACS 0723, an enormous foreground cluster whose combined gravity acts as a natural magnifying lens for much more distant, much older galaxies sitting directly behind it. NASA described it at the time as the deepest, sharpest infrared image of the distant universe ever captured. Webb has continued to study similarly massive galaxy clusters since then, including Abell 2744, sometimes nicknamed Pandora's cluster, because it appears to be the product of multiple smaller galaxy clusters actively colliding and merging together. Webb's deep observations of this region have revealed thousands of extremely faint, extremely distant background galaxies, magnified and distorted by the cluster's gravity, giving researchers a genuinely detailed look at galaxy populations from very early points in cosmic history. None of that requires any hidden pattern, message, or design to be scientifically remarkable. The actual physics involved, massive objects bending spacetime, magnifying and distorting the light of galaxies behind them, letting us see structures we otherwise never could, is already one of the most elegant, well-tested confirmations of general relativity that exists anywhere in modern science. It's worth being directly honest here about something. A significant amount of content online has taken these real Webb discoveries, the little red dots, the precise Einstein rings, the ancient massive galaxy candidates, and dressed them up with claims about hidden signals, deliberate cosmic patterns, or evidence the universe was engineered with a message meant for us to eventually notice. None of that framing comes from Webb's actual, published, peer-reviewed data. What Webb has genuinely confirmed is stranger and more interesting than that kind of embellishment, precisely because it represents real, ongoing scientific uncertainty being worked through by actual researchers, rather than a settled, dramatic revelation. The little red dots are a real puzzle. Nobody knows for certain yet exactly how early supermassive black holes managed to grow so quickly, and that's a legitimately exciting, unresolved question currently driving active research across multiple institutions. The direct exoplanet imaging capability Webb demonstrated with HIP 65426b is real, and it's already been used to study other planetary systems since, opening a genuine new frontier in the search for potentially habitable worlds around other stars. The precise Einstein rings Webb has captured are real, direct visual confirmation of general relativity's predictions playing out exactly as expected, letting scientists measure the mass, including dark matter content, of galaxies with genuinely improved precision. So what does the unimaginable actually mean here in an honest sense? It means a telescope specifically engineered to peer further back in time and see fainter, more distant objects than any instrument before it. And it's succeeding at that mission in ways that are actively generating new questions faster than researchers can fully answer them. That's not evidence of anything hidden or withheld. It's exactly what genuine scientific progress looks like when a powerful new tool starts operating. Established assumptions get tested against real data. Some hold up, some need refining. New puzzles emerge that nobody had fully anticipated, and entire research careers end up built around carefully working through exactly why. Webb's full mission is expected to continue for years, potentially decades, given how efficiently it's used its fuel supply so far. Every additional year of operation means more deep field images, more directly imaged exoplanets, more precisely measured gravitational lenses, and almost certainly more genuinely puzzling early universe objects that will keep astronomers arguing, testing, and refining their models for years to come. That's the actual story behind what James Webb has confirmed. Not a hidden warning, not evidence of design, and not a message waiting to be decoded. Just a remarkably capable instrument, doing exactly the job it was built for, and in the process, generating some of the most genuinely interesting open questions in modern astrophysics. If you want to keep following what Webb confirms next as its mission continues, subscribe and turn on notifications. The real universe keeps turning out to be strange enough on its own, without anyone needing to dress it up as something it isn't. Voyager 2's final transmission just stopped the world for 37 hours in the summer of 2023. NASA genuinely didn't know if it would ever hear from Voyager 2 again. Not because of anything artificial reaching out from the dark. Because of a routine command, one wrong character, and an antenna pointed just 2 degrees off target, 12 billion miles from Earth. Stick around, because the real story here is tense enough without inventing anything. And if you want more real space history, subscribe now. Let's start with why Voyager 2's communication link is so fragile in the first place, because that fragility is central to understanding everything that's happened since. Voyager 2 launched on August 20, 1977. Nearly 5 decades later, it remains one of only 2 human-made objects ever to physically cross into interstellar space. Alongside its twin, Voyager 1, it's the only spacecraft in history to have flown past all 4 outer planets: Jupiter, Saturn, Uranus, and Neptune. Today, it sits more than 12 billion miles from Earth, moving through a region of space nothing else humanity has built currently occupies. And staying in contact with it depends entirely on a network of enormous radio dishes, scattered across the globe called the Deep Space Network. Here's the critical detail that makes Voyager 2 uniquely vulnerable compared to its twin. Because of the specific direction Voyager 2 traveled after its planetary flybys, it moved out of the solar system on a southward trajectory, meaning only ground stations in the southern hemisphere can currently see it clearly enough to send it commands. For years, that meant a single antenna carried an outsized responsibility for the entire Voyager 2 mission. Deep Space Station 43, a massive 230-foot dish located in Canberra, Australia. It was, for a long stretch of time, the only antenna on the entire planet capable of transmitting commands to Voyager 2 at all. In 2020, NASA took that critical antenna offline entirely, for roughly 11 months, to complete essential upgrades and maintenance work. During that period, NASA could still receive Voyager 2's incoming signals through smaller antennas, but couldn't send any new commands to the spacecraft at all. That meant if anything had gone seriously wrong with Voyager 2 during those 11 months, NASA would have had no way to intervene. The spacecraft was, quite literally, flying on its own, completely uncommandable, for nearly a year. Thankfully, nothing did go wrong, and DSS-43 came back online in February 2021, restoring full two-way communication. So what does Voyager 2's actual final transmission look like when it eventually happens? It won't be sudden or dramatic. Engineers expect the process to unfold gradually, much like everything else about this mission's long, slow decline. Instruments will continue being shut down individually as power keeps dropping year after year, exactly as it has for decades already. Eventually, even the spacecraft's basic transmitter and onboard computer will likely lose the power needed to keep functioning at all, and Voyager 2's signal will simply fade below whatever threshold the Deep Space Network is capable of detecting. Mission engineers have expressed hope that at least one instrument on each Voyager spacecraft might remain operational into the early 2030s. But they're equally clear that an unexpected problem, a critical component failure, another communication mishap like 2023's misalignment, but without the extra reserves of time the automatic reset system provided that time, could shorten that timeline considerably. When that final signal does eventually arrive, it won't come as any kind of message or warning. It will simply be the last faint transmission from a machine that's been speaking to Earth for nearly 50 years, growing gradually quieter every single year as its power supply keeps declining, exactly as the laws of radioactive decay always guaranteed it eventually would. Attached to the outside of that same spacecraft, the entire time has been the golden record. Photographs, natural sounds, music from across human cultures, and greetings recorded in 55 different languages, curated decades ago by Carl Sagan and his team. It was never built to power anything, and it isn't part of any active system. It's simply riding along, a deliberate message meant for no audience alive today, drifting through interstellar space long after Voyager 2's own instruments eventually fall silent. That's the real, complete story behind Voyager 2's eventual final transmission. Not an alien contact event, and not a coded warning hidden inside its data. Just an aging, genuinely remarkable machine, still speaking to Earth against every reasonable expectation set back in 1977, fighting a slow, permanent, entirely natural decline in power that engineers have spent decades carefully managing, one difficult decision at a time. If you want to keep following Voyager 2's story as it continues, including whether the 2026 power reconfiguration succeeds, subscribe and turn on notifications. The real story out there is remarkable enough without anyone needing to invent anything extra.